Well, welcome to chapter 3. Um, so we just have a little bit more to do with limit definition of the derivative, and then I can give you the derivative shortcuts. So let's take a look at f of x equals x squared plus x, and let's find f prime of 3. And I'd like to have you do this with all 3 limit definitions of the derivative. So will you first use um, will you first what is this? Oh, I'm sorry. I'm looking at my notes and I'm being confused by them. Okay, so here's what I want to do. F prime of 3 is what I want to find. Okay. So you're going to find the slope at 3 using f of x. And you've got 3 different limit definitions of the derivative to use. Well, I want you to look at what these students have written and tell me about them. So here's the first one. This student says f prime of 3 equals f of x plus h minus f of x all over h. What's wrong with that? Is that f prime of 3? Well, no. This is the average rate of change. It's not even the instantaneous rate of change. If we wanted instantaneous rate of change, we'd need a limit as h heads to 0 here. But wait, there's more that's wrong with this. This finds f prime of x, not f prime of 3. If you want to do f prime of 3, then you'd need either the limit as h heads to 0 of f of 3 plus h minus f of 3 over h, or you could say f prime of 3 was equal to the limit as x approaches 3 of f of x minus f of 3 over x minus 3. This is not the limit definition of the derivative. That's the recipe for average rate of change, and it's not, this average rate of change doesn't say anything about 3. And 3 is a point, and I only use average rate of change on an interval. Oh my goodness, there's so much wrong with this. Okay, so here's the next student. The next student has written this. They have said f prime of x equals the limit as h heads to 0 of f of x plus h minus f of x over h. And then they say that's equal to x squared plus 2xh plus h squared plus h minus x squared minus x. All right, and that's all I write. What's up with this? That's correct. It's interesting. They started off great, and then they just sort of died. The limit needs to be there still. We need to have the limit as h heads to 0 here. And where's my dividing by h gone? Now, do I have f of x plus h here? I plugged in x plus h and FOILed. Good. I plugged in x plus h for this x. Then I have to subtract the x squared plus x, and when we distribute that negative, we get that. So where do we go from here? Will you finish this problem and tell me what f prime of x is? Okay. Did you then have the limit as h heads to 0? The x squareds canceled, the x to the first canceled, of 2xh plus h squared plus h over h. Oh, good. So then we want the limit as h heads to 0 of 2x plus h plus 1 over h. Look, h divided by h is not 0, it's 1. These cancel. Now we can plug in our 0 for h, and we can claim that f prime of x equals 2x plus 1. And so if we want to find f prime of 3, we simply plug a 3 in there. 2 times 3 plus 1 is 7. Great. So I don't know why they didn't finish, but it was a little sad for me. So let's take a look at this student's work. They said that f prime of f prime of 3 was the limit as x approaches 2 of x minus 2 squared plus x minus 2 minus x squared plus x all over x. So what about this person? Well, it looks to me kind of like they're, well, first of all, this is a 3 and these are 2s. So that's a problem. So I'm going to change those to 3s. But let's think about this. It appears as though they're finding the slope at a point, and we've only got 2 choices for that. We've got the limit as h heads to 0 of f of 3 plus h minus f of 3 all over h. And I don't see that here. F of 3 is going to be a number, not this stuff. And f of 3 plus h, that's not 3 plus h. That's not 3 plus h. Maybe they're using the limit as x heads to 3. Oh, I could believe as x heads to 3. And then I would say what? Well, this is supposed to be f of x minus f of 3 over x minus 3. Well, is this f of x? No, that is. And f of 3 is a number. I don't see a number up here. And the denominator is supposed to be x minus 3. I think they're sort of mixing these two together in a really toxic way. So, yeah, don't do that. Don't do that. Instead, f prime of 3, the limit, and I think this is the one they were intending on because of that. The limit as x approaches 3 of f of x minus f of 3, because 3 is 9 over 12, over x minus 3. That's what we should have. And so I've got the limit as x approaches 3 of x plus 4 times x minus 3 over x minus 3. And I get x plus 4, so when I plug in x, I get 7. Okay, how about this one? The limit as x approaches a of f of x minus f of a over x minus a equals the limit as x approaches a of x squared minus x minus a squared minus a over 3 minus a. All right, tell me what's happening here. They're taking x and plugging x into this, and I get that, except that's a plus sign, and this is a minus sign. So there's the first mistake. The first mistake is that. Okay, and then they're supposed to subtract f of a. So f of a is going to be a squared plus a. And I'm subtracting, so minus a squared minus a, that's good. Okay, but this should be a plus. All right, then on the bottom, I notice they say 3 minus a. 3? Why is there a 3? No, this needs to be x minus a. Okay, and then they say this. Then they say 3 squared plus 3 minus a squared minus a over 3 minus a. So it seems like they're trying to now plug in an a value, except they plugged it in for the x's and not the a's. Remember, that a is the specific x value. Our specific x value is 3, then great, I want to plug, yeah, no, it just, oh, they're saying x, no, don't get it. If they had put here the limit as x approaches 3, I would understand replacing the x's with 3's. But we're doing x approaches a. And if we do x approaches a, we're not going to have these. We're going to have a squared, a, and a, and we're going to end up with 0 over 0. And we're going to be sad. Unless we keep going with this. Unless, as I did in that earlier video, we don't do this yet, because we can't. But instead, at this point, we think about factoring. Now, last time I grouped these together and these together. I'm wondering if what happens when I group these together. Do I get anything? Well, I could take out an x and have x plus 1, and I could take out a minus a and have a plus 1. Yeah, that's not getting me anywhere, because I don't have any like terms there. So what I did before was the limit as x approaches a of x squared minus a squared plus x minus a over x minus a. And the reason I did that was so that I could do some factoring. Limit as x approaches a, x minus a, x plus a, plus x minus a over x minus a. And here we see that we have two terms, and we can factor an x minus a out of both x approaches a. So I'll take out an x minus a. What's left over? Well, here I have an x plus a plus, what's here? X minus a divided by x minus a is 1. All over x minus a. So now I can cancel those out. Now I can replace the x's with a's, and I'll get a plus 1, or 2x plus 2a plus 1. Okay, so yeah, please make sure you know your limit definitions of the derivative. All right, how about this dude? F prime of 3 equals the limit as h approaches 0 of f of a plus h minus f of a all over h. And then they said that was equal to the limit as x approaches a of x squared minus x minus a squared minus a. But wait, that's supposed to be a plus. Okay. They did that. No, they didn't do that. Sorry. They said that's going, what? Sorry. Backing it up. The limit as h approaches 0 of f of a plus h minus f of a all over h. That's what they did. And that equals the limit as h heads to 0 of a plus h squared plus a plus h minus a squared plus a all over h. So what mistake did they make? Well, they plugged in an a plus h for all the x's in f of x, and remember our f of x is x squared plus x. Okay? So if I take a plus h and plug it in there, and a plus h goes in there, I get that. And then I'm supposed to subtract f of a. So what's f of a? F of a is a squared plus a. And I'm supposed to subtract f of a. See, subtract f of a. So when I subtract f of a, I do get a minus a squared, but I also get a minus a. They don't have minus a. And because of that, the whole rest of their work is going to be wrong. So, will you please finish this problem properly? And remember, we're trying to find f prime of 3. Oh, by the way, this here, yeah, that's a problem. Because you've now told me that these things are supposed to be equal, and they're not equal. If you want to say f prime of a equals this stuff, that's legit. That's okay. But if you say f prime of 3 is equal to this, no, no, it's not. That's called a linkage error in College Board language. So a linkage error occurs when you try and claim the two things are equal when they aren't. F prime of 3 is not this. This is called f prime of a. Okay, so now finish off this problem and tell me, remember what we were trying to do here was find f prime of 3. Okay. Hey, welcome back. So, did you do the limit as h heads to 0 of a squared plus 2ah plus h squared plus a plus h minus a squared minus a all over h? And then did you say that's going to be the limit as h heads to 0 of the a squareds cancel and the a to the firsts cancel? So we have 2ah plus h squared plus h over h. And so we can take out an h from the numerator and have 2a plus h plus 1. Please don't lose that 1 over h. And now we can plug in our 0 for h and get f prime of a equals 2a plus 1. But remember, we want f prime of 3, so we're going to do 2 times 3 plus 1, or 7. All right. Whew. Finding other people's mistakes, that's a challenge. And, you know, they would have, in fact, I can show you the rest of their work. They went on and said this. They said the limit as h heads to 0 of a squared plus ah plus h squared plus a plus h minus a squared minus a all over h, and then they combined like terms and said the limit as h heads to 0 of ah plus h squared plus h over h. And then they said that was the limit as h heads to 0 of a plus h plus 1. Well, so I like that they remembered the distributing. They caught it later. They didn't catch it at first, but they fixed it later. But now there's another mistake. Because when they FOILed, this is a plus h times a plus h, they're supposed to have 2 ah here. And without that 2, they're going to get the wrong answer. Okay. So with chapter 3, we're going to talk a little bit more about the derivative, and we're going to then move on to our derivative shortcuts. I think we've reviewed the limit definitions of the derivative enough, but I'm going to do it one more time. H heads to 0 of f of x plus h minus f of x over h. There's our general derivative. It finds f prime of x. But maybe we want to know f prime at some point. And so then we would have the limit as h heads to 0 of f of a plus h minus f of a over h. Or we could use that other limit definition of the derivative at a point and say the limit as x approaches a of f of x minus f of a over x minus a. So we need to be really comfortable with these, and you're going to be doing a lot with these on the next test, on the Chapter 3 test. Even though there will be lots of shortcuts to use, we're definitely going to be still using limit definition of the derivative. Now, derivative notation. Let's say I've got y equals f of x, and I want to talk about the derivative. Well, I can talk about this derivative in lots of ways. First, I can call y prime the derivative, or I could say f prime of x is the derivative. I could also say take the derivative of y with respect to x. Take the derivative, in fact, it's not, it's just the derivative of y with respect to x. That's what that means. Or I could have df dx. This is again the derivative of f of x with respect to x. Okay? So I've got a bunch of different ways to describe the derivative. There's one more, though. These are all nouns. Hi, I'm the derivative of y. Hi, I'm the derivative of f. Hi, I'm the derivative of y with respect to x. Hi, I'm the derivative of f with respect to x. These are all noun forms. Well, there's also a verb form. D, dx, y. When I see this, this is the imperative form, the command, and it commands you to take ye the derivative of y with respect to x. It's a command. Take that derivative. Okay, so this is the verb form. All the others are nouns. All right. So, oh, let's say I want to know the derivative of f of x equals y at x equals 1. So there's some notation for this too. We could say y prime of 1. We could say f prime of 1. We could also say dy dx evaluated at x equals 1. Or df dx evaluated at x equals 1. Okay? So all of these mean the same thing. Evaluate the derivative at x equal to 1. Okay. Now, we're supposed to know how to do this stuff on our calculator. We talked about finding dx of x squared plus x. No, I don't want to say that. I want to say y equals, oh, I remember doing this one with cosine x plus 1. And I want y prime of pi over 2. Okay, and so we say, well, we don't know how to do limit definition of the derivative with trig functions. I mean, if I try to, I have the limit as h heads to 0 of cosine x plus h plus 1 minus cosine x minus 1 all over h. And yeah, I can do those, but no, I can't do anything with these. There is a path where I could use something we didn't learn in trig called sum and difference formulas, but that still brings you to a place, even when you use it, it's really horrible. So let's reach out for our calculator at this point, and let's take a look at finding that derivative. Oh, look, there it is. Cosine of x minus 1. Oh, let's change that to minus 1. At pi over 4. Oh, pi over 4. So remember, it was n deriv of, you type in the function in terms of x, and then you type in the point where you want to know the derivative. New calculators do d box of evaluated at x equals box. So this one goes here, and this one goes in here, and the function goes there. Okay? And yeah, make sure you can take the derivative of that on your calculator at pi over 4, and I got negative 0.707. So just for you to check your work, you might want to pause the video and check. But actually, you know what I want to do right now? It's not evaluate a derivative that I want to do right now. It's graph a derivative. Okay, so earlier we were talking about this function, x squared plus x. And let's say I want a graph of f prime of x. Well, thank you, Magic Box. Go to y equals, type in x squared plus x. Now go to y2, go to math, go up to n deriv, and now say you want the n deriv of y1, comma x, comma. Now, because we want to graph the derivative, we don't want to know just the derivative at one point. We want to know the derivative at all points. So we're going to replace the number that we would normally plug in here with another x. Okay. I'm actually going to turn this off for a moment and just do zoom standard. So here's our original graph. It's a parabola. And now I'm going to graph on top of that the derivative graph. Ooh, you can't see that. No, you can. All right, so look what I notice. Here I have a negative slope. Oh yeah, that's why these y values are negative. At this point on the parabola, I have a zero slope. That's why there's an x-intercept on y prime. And over here I have positive slopes, which is why this is positive. So, 1, you should be able to graph f prime on the calculator. That's definitely a must for the AP exam. Okay, now what else do we know? Well, we now have the ability to think about sketching derivatives by hand. So let's take a look. Boom. Okay, this is 1, 2. This is 3, 2. This is 5, negative 1. And this is 6, negative 1. And this is, of course, 0, 0. So here's f of x. But let's say I want a graph of f prime of x. Well, we know that f prime of x represents the slopes of f of x. Well, what can we say about the slope from 0 to 1 on f of x? Well, slope is rise over run. I go up 2 and over 1. So the slope is 2, up 2 over 1. So if I'm making an f prime graph, 1, 2, so here's 2, and I've got a slope of 2 until I get to 1. Okay, and then what's my slope from 1 to 3? From 1 to 3, I have a slope of 0. And then from 3 to 5, well, it looks like I go down 3 and over 2. Down 3 and over 2. So negative 1.5. And then that goes until 5. And then from 5 to 6, I have a slope of 0 again. Now, I want to talk to you a little bit about all these open circles. Why do I have these open circles? Well, can the derivative exist at this point? And let's go back to our definition of the derivative. The limit as x approaches 1 from the negative side of f prime of x equal the limit as x approaches 1 from the positive side of f prime. Now what does that mean? That means the limit of the slopes. What can we say about the slopes as we approach 1 from the negative side? Well, we said the slopes over here were 2. And here, as we approach x from the positive side, approach 1 from the positive side, well, as I approach from the positive side, the slopes are 0. Does 2 equal 0? No, the limit of the slopes is not the same. And because the limit of the slopes from both sides is not the same, Therefore, the limit as x approaches 1 of f prime does not exist. Remember, for the limit to exist at a point, the limits from both sides of that point have to be the same. They're not, therefore the limit at the point can't exist, which means the derivative, f prime, the slope at that point can't exist. That is an undefined slope. That is an undefined slope. That is an undefined slope. Okay, because the limit of the slopes from both sides at all of those points aren't approaching the same value. Over here, we're approaching -1.5. Over here, we're approaching 0. Those aren't the same number. So I can't have a derivative here, here, or here, which is why I've got these open circles there. Now at the end points, no problem. The slope here is 2. The slope here is 6. But if I were to extend my graph further and go off in another direction, well, then maybe those would turn into open circles. Okay, so I'd like to spend a little time now talking actually not about whether the derivative exists or not. We'll come back to that in a minute. I actually want to think about doing some graphing. Okay, and I'm not going to give you a function. I'm just going to give you this and say, here's f of x. That's x equals a. That's x equals b. Okay, and this is a graph of f of x, but I want to graph f prime. F prime of x. And here's how I do it. I start with graphing 0 slopes. Okay, so here's a 0 slope, here's a 0 slope. So those are both going to be intercepts on the f prime graph. Now what can we say? Well, from here, the slopes are a little negative, and then they're more negative. This is about as negative as they get. Then they get less negative, and they head back to 0. So said about here was the steepest slope, so the most negative on the slope graph. Okay, y, look, these are all negative y values, and these negative y values on f prime represent the negative slopes on f. The negatives, these y values, represent these negative slopes over here. This is a little negative, this is more negative, this is most negative, then a little less negative, still less negative, almost 0, and back to 0 again. Okay. What about on this side? Well, I see very positive slope, and a less positive, and a little less positive, and almost 0, and almost 0, and 0 slope. So very positive, less positive, less positive, almost 0, 0 slope. The y values on f prime represent how slope, the slope numbers on the red f of x graph. Okay, and then what about here? I see 0 slope, slightly positive, more positive, very positive, exceptionally positive. And so there's my graph of f prime. And it looks like if f was a third-degree polynomial, f prime is a second-degree polynomial. All right. So I'd like to do a little more practice with that, with taking a graph of f and sketching f prime from it. Okay. Hey, what if I had this one? What am I doing? Yeah, I should just do this. No, that's too confusing. That's what I'm looking for. Okay, so this is a graph of f of x. And now I want a graph of f prime. So I start with plugging in 0 slopes here and here. I have some 0 slopes. Now, from here to here, what can we say about the slopes on the black f of x graph? not the y values. I don't care that this is below the x-axis. I don't care that this is above the x-axis. I'm just looking at the slopes on the black y equals f of x graph. So I've got a zero slope, a slightly positive slope, more positive slope. This looks like where the maximum positive slope is, because then these slopes are still positive, but they get less positive. So I think I'm looking at something like that. Okay, and then what about over here? I see a very negative slope. It's true I see a very positive y value, but I don't care about the y value here. I care about the slope. And the slope here is very negative, less negative, even less negative. Oh my goodness, so close to zero, zero slope. Very negative, less negative, even less negative, heading to zero, zero slope. And over here, I see the same thing. I see a little negative slope and a bigger negative slope and a very negative slope. And so my graph looks like this. And isn't it interesting that f prime of x looks like a downturned parabola for this f of x, which looks like a negative x to the third graph? I wonder if there's something to that. All right, so will you try this one? I guess I want to start here. And let's call that, no, I'll let you call that. Okay, so this is a graph of f of x. Will you please draw on top of this f prime of x? F prime of x. Pause the video if you haven't already. Go off and give it a try. Come back when you're done. Hey, welcome back. Did you start with putting in these zero slopes? Here, here, and here. Now, between this point and this point, I'm looking at this. A little negative, more negative, most negative, less negative, heads back to zero. Remember, the red graph is f prime, the derivative of f, also known as the slopes of f. So these y values that I'm sketching in here, these would be the slope numbers at each of those points. All of these slopes are negative. This is where I have the most negative slope, which is why this is the most negative y value. From this point to this point, though, near zero slope, getting a little more positive, even more positive. That's as positive as it gets. And then these are still positive slopes, but they're heading back to zero. Okay, now over here, a little negative, more negative, very negative, extremely negative. And over here, these are all positive slopes, extremely positive, less positive, still positive, but less than that one. Almost zero, but positive. So that's going to be this. So now, there was my f of x. It looked like a fourth degree polynomial with a negative leading coefficient. And what can we say about our f prime of x? It looks like a negative third degree polynomial. So something that is in fact true for polynomial derivatives is the derivative of a polynomial will be 1 degree lower than the original function. So if I've got an x squared function, then I'm going to have a y equals x kind of linear derivative. If I have a fifth degree function, the derivative will be fourth degree. And that's nice, because we will spend some time with polynomial derivatives, but they're derivatives of all kinds of functions. trig functions, log functions, exponential functions, square root functions, inverse trig functions. I mean, so many. So yes, this is true, but it's a limited use tool because there's so many different types of functions. Okay, let's do one last one. One last one? No, because we still have all these one-sided derivatives to get through. Okay, so I want to ask I want to ask, how do we know HD, how do you know YK? How do you know if a derivative exists at a point x equals a? How do you know? How will I know? Well, there's two real requirements here. The first one is f of a must exist. Because if the point doesn't exist, you can't have a tangent line there. But I think even further, I want to say that f is continuous at x equals a. And this is included in that. So let's just say f has to be continuous at that point. But just because the function is continuous at a point, for example, let's consider y equals absolute value of x. What's the slope over here? Well, that's a slope of 1. What's the slope over here? That's a slope of negative 1. And what can we say about the limit as x approaches 0 from the negative side of f prime compared to the limit as x approaches 0 from the positive side of f prime? What can we say about the limit of the slopes? Well, this slope is always negative 1, and this slope is always positive 1. So can the limit as x approaches 0 of f prime exist? Oops. No. Because these limits are not equal. So that's going to be the second thing that we need. The limit of the slopes from both sides has to be equal to each other, because if the limit of the slopes isn't the same from both sides, then the limit at the point of the slopes won't exist, and therefore our derivative can't exist, because remember, our derivative is a limit. Our derivative is the limit. So we could actually expand this and write the limit as x approaches 0 from the negative side of f of x. And it's time for the marker. F of x minus f of 0 over x minus 0. Does that equal? Not in this case. The limit as x heads to 0 from the positive side of f of x minus f of 0 over x minus 0. Okay, so think about what we've got going on here. We've got, this is the slope of f at 0 from the left. This is the slope of x at 0 from the right. We need these slopes to be the same. But in our problem, absolute value of x, we saw that they weren't going to be the same. This is going to be a slope of negative 1. This is going to be a slope of positive 1. The limit of the slopes is not the same. Therefore, the limit, the limit as x approaches 0 of f of x minus f of 0 over x minus 0. This does not exist. This limit definition of the derivative, this does not exist. F prime of 0 does not exist because the limit of the slopes from both sides isn't the same. Now, I will tell you that instead of writing that out, I would much prefer to to say the limit as x approaches 0 from the negative of f prime doesn't match the limit as x approaches 0 from the positive of f prime, right? I can summarize that whole difference quotient piece to just saying, yeah, the limit of the slopes isn't the same from both sides. Therefore, the derivative does not exist at x equals 0. Okay, so two things are required for the derivative to exist. One, the function has to be continuous at that point, and two, the limit of the slopes from each side of that point have to be equal to each other. Okay, the slopes have to be approaching the same number. So let's take a look and ask the question, does f prime of 2 exist? Okay, let's just ask about existence. So f of x is defined this way. X squared minus 2x plus 3 for x values less than 2, and 2x minus 1 for x values greater than or equal to 2. And I want to know if f prime of 2 exists. So what are the requirements for f prime of 2 to exist? Well, we know we need the limit as x approaches 2 from the negative side of f prime to equal the limit as x approaches 2 from the positive side of f prime. That's one of the things that we need in order to know if f prime of 2 exists. So let's go about using our limit definition of the derivative on this and using our limit definition of the derivative on this to find what would be the limit of the slopes from both sides. Okay, so if I start with this side, I'm going to have the limit as, and I want to know about 2. Yeah, I'm actually going to go with this one. F of x plus h, x plus h squared minus 2x plus h plus 3 minus f of x squared minus 2x plus 3 all over h. This is going to find f prime of x for me, but only for x is less than 2. So that's going to be the limit as h heads to 0, x squared plus 2xh plus h squared minus 2x minus 2h plus 3 minus x squared plus 2x minus 3 all over h. Okay, so these can cancel, these can cancel, these can cancel. Where does that take me? Wow. That takes me to this place. The limit as h heads to 0, 2xh plus h squared minus 2h all over h. And that's going to be the limit as h heads to 0 of h, 2x plus h minus 2 over h. And now I can plug in my 0 for h, and I get that f prime of x is 2x minus 2. So the derivative of this is 2x minus 2. Oh, look, the derivative is 1 degree less than this. That's very interesting. I wonder what will come of that. All right, so we want to know f prime of 2. So that's 2 times 2 minus 2 is 2. So the limit as x approaches 2 from the negative side of f prime is 2. The limit of the slopes from the left is 2. Well, let's go through and repeat this process now with the right-hand side. So now we're looking at the limit as x approaches, h approaches 0 of f of x plus h, so 2x plus h minus 1 minus 2x minus 1 all over h. And so that's going to be the limit as h heads to 0, 2x plus 2h minus 1 minus 2x plus 1 all over h. Again, the two x's cancel, the 1's cancel, the h's cancel, and I get 2. And really, that shouldn't be a surprise to me, because what's the slope of this linear equation? 2. And so what we just found then was the limit as x approaches 2 from the positive side of the slopes. The limit of the slopes from the right-hand side is 2. The limit of the slopes from the left-hand side is 2. And since the limit of the slopes from both sides are equal, and they're both equal to 2, then I kind of want to say that the derivative at 2 is 2. However, there was a second requirement, not just that the limit of the slopes from the positive and negative side be equal, which they are in this case. What was the second requirement? The second requirement was that f is continuous at x equals 2, or more general, x equals a. So, is this function continuous at 2? Well, let's check. Let's see now. Now let's see, we're not talking about slopes. We're talking about continuity. So I want to know the limit as x approaches 2 from the negative side of f, not f prime, of f, the y values of the original function. Do they equal the y values as x approaches 2 from the positive side of the original function? Well, if I plug a 2 in here, I get 4 minus 4 is 0 plus 3 is 3. And if I plug a 2 in here, 2 times 2 is 4, minus 1 is 3. And does f of 2 exist? F of 2 is 3, because I'd be plugging 2 into this piece, not this piece. So remember, since these are equal, we know that the limit as x approaches 2 of f exists, and we know that limit is equal to 3. And that's also equal to f of 2. This was our requirement for continuity, remember? This had to exist, this had to exist, and these numbers have to be the same. Well, we found out that the limits were 3 from both sides, so we know the limit exists. And at 2, the y value is 3, so the point exists. This is 3, and therefore, since they're both 3, we know that the derivative exists at x equals 2 on this graph. This function has a derivative at x equals 2. But what about this function? Here's our f of x. F of x equals x squared for x is less than or equal to 1/2, and x for x is greater than 1/2. And here I'm looking for f prime of 1/2. Does f prime of 1/2 exist? Well, let's take a look. The limit as x approaches 1/2 from the negative side of the slopes. What's the limit of the slopes going to be coming from the left? It's going to be the derivative of this, which is going to be the limit as h heads to 0 of x plus h squared minus x squared all over h. And so that's going to be the limit. Ooh, that's a linkage error, because this is the general derivative. And I'll need to plug 1/2 in. Okay, so h heads to 0 of x squared plus 2xh plus h squared minus x squared over h. And so we're going to get the limit as h heads to 0. The x squareds cancel, 2xh plus h squared over h. And then we can pull out that h from everywhere. The limit is h heads to 0 of 2x plus h. And when I plug a 0 in for h, I get 2x. So the slope machine, f prime of x, as x heads to 2 from the negative side, I'm sorry, not 2, but 1/2 from the negative side, that f prime of x is 2x. Okay, so what happens if I want to know f prime of 1/2? Well, that's 2 times 1/2, or 1. So I know that the slopes are approaching y equals 1, or the slopes are approaching a value of 1, as we approach x equals 1/2 from the negative side. Well, what about pursuing the other side? What about the slope from the positive side? I want to know the limit as x approaches 1/2 from the positive side of f prime of x. So let's check the slopes on the positive side. The limit as h heads to 0 of x plus h minus x over h. Well, I get 1, right? Because these cancel, and h divided by h is 1. And that doesn't surprise me because I see a linear function here. The slope of this linear function is 1. So of course it's 1 here. So this slope is 1. Hey, look. What do we notice about the limit of the slopes? The limit as x approaches 1/2 from the negative of f prime is 1, and the limit as x approaches 1/2 from the positive of f prime is also 1. So because the limit of the slopes exist from both sides and are equal to each other, we can say the limit as x approaches 1/2 of f prime exists. But that still doesn't tell me whether f prime of 1/2 exists. What was the other requirement? Besides the limit of the slopes had to be the same from both sides, what else did we need? We needed continuity. And that's why we learned about continuity in the last chapter. So, is f continuous at x equals 1/2? Well, in order to know that, we need to know that f of 1/2 equals the limit as x approaches 1/2 from the positive, not of f prime, not of the slopes, of f, of the actual y values. And this should equal the limit as x approaches 1/2 from the positive side of f. Or, more concisely, does the value of the point equal the value of the limit at that point? Well, let's check out the limit as they can't both be plus. The limit of the function as we approach x from the positive side. That's the positive side. We approach, we plug a 1/2 in there, and we get 1/2. Well, what about plugging in a 1/2 as x approaches 1/2 from the negative side? Well, I get 1/2 times 1/2, which is 1/4. Are these equal? No, they're not equal. So these aren't equal. So this does not exist. And because this does not exist, we are not continuous. And if we're not continuous at that point, then we know that the derivative at that point cannot exist. Let's just do two more things with this problem. Let's say, okay, look at a graph. Here's my graph. We're going up to x squared. That's 1/4 there at 1/2. And then y equals x at 1/2. Well, if I plug a 1/2 in, I get a 1/2 out. And so there's the other part. They both at this point, see, these are kind of parallel. They both at this point have a slope of 1. But even though the limit of the slopes is the same coming from both sides, since the function is not continuous, we say the derivative doesn't exist. There can be no f prime of 1/2 here. And so this is what I would write, and this is what you'll need to write in the next test. F prime of 1/2 does not exist because while the limit as x approaches 1/2 from the positive side of f prime does equal the limit as x approaches 1/2 from the negative side of f prime, because while the limit of the slopes is equal, f is not continuous at x equals 1/2. Okay? So there's two requirements for differentiability. Differentiability requires two things. The first thing it requires is that the function is continuous at the point. The second thing that we need, since the derivative is a limit of the slope formula, that limit can't exist unless the limits from both sides are the same. So we need the limit of the slopes to be the same from both sides of our point, and we need the function to be continuous. Okay, let's go further. How about this one? F of x equals x squared for x is less than or equal to 2, 2x for x is greater than 2. And I want to know f prime of 2. Okay. Do you feel up to it yet? If you do, pause this video, give it a try, because you'll definitely have a question like this on your next test. Alright, first, let's check continuity. The limit as x approaches 2 from the negative side of f should be equal to the limit as x approaches 2 from the positive side of f. So, if I plug a 2 in here, I get 4. If I plug a 2 in here, I get 4. And f of 2 is also 4. So I know this function is continuous at x equals 2. But what about the limit of the slopes? Okay, so I'm going to check the limit of the slopes now. Let's check from the left side. The limit as x approaches, we could do this, x approaches 2, x squared minus 2 squared over x minus 2. And that's going to be the limit as x approaches 2, and I guess we're coming from the negative side, of x minus 2, x plus 2, right, because that's a 4, and x squared minus 4 is this difference of squares, over x minus 2, cancel, and plug my 2 in. And what do I get? I get the limit as x approaches 2 from the negative side of f prime. I get the slope to be 2 plus 2 or 4. Okay. Well, what about the limit of the slopes from the other direction? What if I want to talk about the positive direction? Will that change things? Well, I'm going to have 2x minus f of 2, which is 4, over x minus 2. So here I've got the limit as x approaches 2 from the positive side of 2, x minus 2 over x minus 2, and I get 2. And I get 2. So the limit as x approaches 2 from the positive side of the slopes, the limit of the slopes from the other side, is 2. Do the limit of the slopes from both sides equal the same number? No, they do not. So guess what? I know that f prime of 2 does not exist. Okay? I'm using one-sided derivatives to show this. I'm using a derivative from the positive side. I'm using the derivative from the negative side. I'm using one-sided derivatives to figure this out. Okay? All right, there'll be more on this in an upcoming unit. Anything else I want to cover? F prime. Yeah, let's do this. Let's do a couple more problems. Here's given f prime, come up with a continuous f of x. How am I supposed to go backwards? Well, here. I'm not going to be too horrible to start with. X less than 1, x greater than or equal to 1. So there's our f prime. Remember, f prime represents the slopes of f of x. So this is a slope. What function has a slope of 3 everywhere? Well, couldn't we say f then equals 3x for x values less than 1? Yeah, why not? Because what's the slope of this? The slope of this is going to be 3 everywhere, and that's what that says. So what can I write for this part? Well, this is a slope. So how about negative 2x for x values greater than or equal to 1? However, while I agree that the derivative of this is this, and the derivative of this is this, remember here it says continuous f of x. Is f of x continuous at 1? So let's take a look. If we plug 1 in here, we get 3. If we plug 1 in here, we get negative 2. Does 3 equal negative 2? Why, no. So the limit of the function from both sides of 1, that doesn't touch. So remember how it said come up with a continuous f of x? Well, I plug in a number here, and I get 3. Here, I get negative 2 when I plug in that same number. I want these to be the same. So maybe if I've got a 3 and I want a negative 2, I need this. Because if I plug a 1 in here, I get negative 2. If I plug in a 1 here, I get negative 2. And so the y values would be the same. But wait, does that throw off our derivative? What's the derivative of a constant? Here's the line y equals 5. What's the derivative or slope of that line? No, the slope is 0 there. And the slope here is 3. So, yeah, this builds that. Now, I could put a minus 5 there, or I could put a plus 5 here and say, okay, now when I plug in a 1, I have negative 2 plus 5 is 3, and that's the same as I have over there. So it's not just turning these into linear functions, but I also have to check the composition. I think you see one of those in the homework. Let's make this be a little more, a little easier, so you don't have to guess at which one to add what to. Let's say that whatever the f of x is, f of 1 has to equal 4. Okay, so we said that f of x would be 3x for x is less than 1, and negative 2x for x is greater than or equal to 1. If I plug in a 1 here, I should get 4, but I don't, I get 3, so I better add 1. If I plug in a 1 here, I should get 4, but I don't. I get negative 2, so I have to add 6. So this f of x has f of 1 equals 4. Both of these approach the same value, so the limit of the function is 4. The value of the point is 4 at 1. And we know the derivative of this would be this, and the derivative of this would be this. So there's a great f of x for us. Now I think maybe you should try them. Okay? We're still going to come up with an f of x. But I'm going to tell you that f of 2 equals 3, and that f prime of x equals negative 4 for x is less than 2, and 2 for x is greater than or equal to 2. Please come up with an f of x that meets this condition and this. Pause the video, come back when you're done. Okay, so I'm thinking these are constant slopes. Linear functions have constant slopes. Now, I need to pass through that point with both of these pieces. If I plug in a 2, I should get 3. If I plug in a 2 here, I get negative 8, but I want positive 3, so I have to add 11. If I plug in a 2 here, I get 4, but I want 3, so I better subtract 1. So there's my possible f prime. This idea of going backwards from f prime to f, that's going to be a really big important topic for us next semester. Right now, though, we're not going to do that much with it, so you don't have to worry about it. Okay, I kind of want to do a little more limit definition of the derivative stuff. How are we doing for time? Oh, we're already at 1:09. I guess I'll wait until the next video. So, I hope this has been enlightening, and that things with the derivative are moving along. All right, I promise the shortcuts are coming soon. Take care, everyone.